So let us check if Rn with this function d2, we will call this function as d2. We will define this function as d2. So this 2 only to represent the power. Okay, here it is 2 and here it is 2. So just giving it a notation with that. So we are defining. So let us check if Rn with this d2 is a metric or not. For Rn to be a metric, it must satisfy those 4 conditions. So first of all, let's check non-negativity. What we have to show in non-negativity, that for every x and y in Rn, d of xy should be non-negative. So this is something we have to show for every x and y in Rn. So let us consider any 2 points x and y from Rn arbitrarily. So x, which looks like ordered n tuples, y which looks like ordered n tuple, be any 2 element in Rn. Okay, so what I have to show is distance, d of xy is non-negative. Okay, so how we have defined d of xy? What we have to show that d of xy is greater than equal to 0, we have to show that summation xi minus yi square I running from 1 to n power half is non-negative by definition of d2xy. Okay, so since when we defined this at Rn, what we defined it as the collection of all ordered n tuple where each tuple, each element, where each element in this tuple belong to the set of real numbers. So xi and yi both are in real numbers, and this is for every I running from 1 to n. Since xi and yi both are in R, therefore their difference is also in R since R is closed under difference. So xi minus yi is in R. Since this is in R, in square of every real number is non-negative, therefore xi minus yi square is non-negative. This is for every I from 1 to n. Since all of these terms are non-negative, that means their sum is also non-negative. This is what I have written, that sum of xi minus yi square where I is running from 1 to n is also non-negative. Since this is non-negative and square root of any non-negative term is also non-negative, therefore d of xy is not negative. Since x and y were chosen arbitrarily, therefore d of xy is non-negative for every x and y belonging to Rn. Now let's check identification. For identification, what do I need to show? That for any x and y in Rn, d2 of xy is 0 if and only if x and y are equal. So consider d2 of xy to be 0. This can only happen by definition if and only if the definition of d2xy, that is summation xi minus yi square I running from 1 to n power half is 0. Now under root of something is 0 if and only if the value inside the root is 0. Therefore this is if and only if summation I running from 1 to n xi minus yi square is 0. Now this is a real number and square of a real number is always non-negative. Sum of non-negative terms is 0 if and only if each of the term is 0. Sum of all non-negative term, none of them is negative. So if all of the terms are non-negative and their sum is turning out to be 0, that means each of the term is 0. That means xi minus yi square is 0 for every I running from 1 to n. And what does this mean? A square of a real number is 0. That means the number inside the square is 0. That means xi minus yi is 0. And what does this mean? This can only happen in real number if xi and yi are equal. And this is for every I running from 1 to n. For every I running from 1 to n. That means, how do we define x? We had defined x as x1, x2 and xn, and we had defined y as y1, y2 and yn. We are saying that xi is equal to yi for every I running from 1 to n. That means x1 and y1 are equal, x2 and y2 are equal, x3 and y3 are equal, so on up to xn and yn are equal. If all the corresponding coordinates are equal, that means we can say that x and y are equal. This is if and only if x and y are equal. So identification is also true. Now symmetry. What does symmetry say? That for every x and y in the set Rn, d of xy should be equal to d of yx. That means interchanging the element does not changes the value. So let us consider x and y from Rn arbitrarily. X looks like x1, x2 up to xn. Y looks like an ordered n tuple y1, y2 up to yn. So d of xy by definition is summation I running from 1 to n xi minus yi square under root. Okay. So if inside a square I interchange these two terms, that will not change the value, right? Because a square xi minus yi is same as a square of yi minus xi. So I can interchange the value. So I have interchanged it and written it as yi minus xi square. By definition, this is d of yx. So symmetry was trivial. Symmetry is trivial. We have nothing to prove for it. So d of xy is same as d of yx. And since xy were chosen arbitrarily, that means that is true for every x and y in Rn. Now next is triangles inequality. Before moving to triangles inequality, let me recall what Minkowski's inequality was. Minkowski's inequality says that if you have collection of xi and yi, if xi and yi are collection of real numbers, then for every p which is greater than equal to 1 and less than infinity, we have summation of absolute value of xi plus or minus yi to the power p, where I is running from 1 to n to the power 1 by p. If we have this condition, then this is always less than equal to summation of mod xi to the power p I running from 1 to n 1 by p. And similarly, summation I running from 1 to n mod of yi to the power p to the power 1 by p. You can just see it as, if you have this condition, you can separately write x and y under this summation sign. Once you can write modulus of xi, and the second time you can write modulus of yi. You can separate these two. That will make this inequality more easier to remember. So in triangles inequality, let us consider three elements from Rn. So x, y and z belongs to Rn. How does an element of Rn look like? X looks like x1, x2 up to xn. Similarly, y is y1, y2 up to yn. Similarly, z is z1, z2 up to zn. Where each xi, yi and zi belong to Rn for every I running from 1 to n. Now since xi, yi and zi, all of these are from R, that means their difference is also from R. So now let us consider d of xy. Wherever I am saying d in this case, that means d2. This is how I have defined the function. So d2 of xy is, by definition, summation I running from 1 to n xi minus yi square to the power half. Can I add and subtract zi in this? Will that make a change? No, that will not. So I can subtract zi and I can add zi. Okay. So now let us write it as one term and it as other. So I have written xi minus zi plus zi minus yi square. Okay. So now square of any real number is same as a square of its absolute value. So can I put here an absolute sign? Will that make a change? No, that will not. So I can simply write it as changing the bracket into the absolute sign. Okay. So inside it I have written the same thing. This is a real number. Can I represent it as ai? This can be written as bi. What I have written in Minkowski's inequality, that I can separate whole of this for ai and for bi. So this is less than equal to summation I varying from 1 to n ai mod ai square. Mod ai is mod of xi minus zi square to the power half plus summation I going from 1 to n mod bi square power half. Mod bi is mod of zi minus yi. By definition, okay. So this is mod. If I remove the mod, will that change a value? No, that will not, because it is always, because a square of a term is always positive. So keeping mod or removing mod will not make any difference. So this is by definition d of xz, and by definition this is d of zy. Therefore d of xy is less than equal to d of xz plus d of zy for every xyz in Rn. Since all four properties are holding with this function, therefore Rn with D2 is a metric space. The distance formula that we discussed was called a Euclidean distance formula. Therefore, this metric that we defined using that distance formula is called a Euclidean metric, and hence Rn with D2 is called a Euclidean metric space. Thank you so much for watching.